Welcome back. In part 1 of this lecture, we met Isaac Newton and described his 3 laws of motion: the law of inertia, the law of forces and accelerations, and the law of forces coming in equal and opposite pairs. The first, second, and third laws provide us with a complete description of the motion of any objects under the influence of forces. We now turn to the question of what is the force that is relevant for trying to understand planetary motions, what we now know as the force of gravity. To understand the force of gravity, we have to go back to original work by Galileo Galilei. Prior to his telescopic work, Galileo did a great deal of fundamental work and research on the properties of objects in motion. In particular, he performed experiments by dropping weights or sliding them down inclined planes and measuring how fast they fell. Out of this work, he discovered what came to be known as the law of falling bodies. This can be stated as follows. In the absence of air, heavy objects and light objects fall with the same constant rate of acceleration. If I held a bowling ball and a baseball in my hand and dropped them to the ground from the same height, despite the tremendous differences in their mass, they would in fact hit the ground at the very same time. There is a legend that Galileo tested and later demonstrated this by climbing to the top of the Leaning Tower of Pisa. He was, after all, a professor at the University of Pisa at the time of this work, and dropping different size weights, sometimes the story is different size cannonballs, and showing that they impacted the ground at the same time. There's no record of this experiment in any of Galileo's notes, nor in the letters or writings of his contemporaries, so it's very likely a story made up in later centuries. But nonetheless, it has a certain ring of truth to it. This kind of relentless experimentation was what Galileo was best known for. More precisely, he would have performed these experiments before his colleagues to make a very particular point. The Aristotelian view of physics held that the reason that an object fell to the earth and eventually came to rest is because objects on the earth, ultimately being made of the element of earth, wish always to go back to the earth, and that their natural state of motion is rest. If I set them in motion, they don't stay in motion for very long because anything I throw or run or roll across the ground eventually comes to stop. Therefore, rest must be a natural motion, and motion, putting things, throwing things, making things go up in the air, that's unnatural somehow, and the object seeks to return to its natural state of rest. Furthermore, because heavy objects are mostly made of earth, if the bigger the object, the more it has the impetus to make its way to the ground. The more stuff there is, the more of that earth stuff there is trying to make it back to a state of rest. And so Aristotle would have reasoned a bigger object should fall to the earth faster than a smaller mass object. Galileo showed that this in fact was not correct. One could argue, correctly however, that what Aristotle was really talking about in many of these descriptions of falling objects was objects falling through thick media. For example, 2 different sized rocks sinking to the bottom of a pond will behave differently than 2 rocks dropped in the air. A rock and a feather dropped together, well, we know what will happen there. The rock will fall quickly, and the feather, floating on air, will have to slowly waft its way to the ground. Galileo, however, saw through this as mistaking the medium that they're falling through as controlling it, as merely interfering with what should have been the natural motion, and that natural motion should have been to fall to the ground at exactly the same constant rate of acceleration. In other words, the resistance of air is what we would call today a second-order effect, but the real fundamental motion was constant rate of acceleration in the influence of gravity. Well, Galileo could not do the experiment in his time by showing how 2 objects, like a hammer and a feather, could fall under the influence of gravity because he could not go to a place that was airless. We don't have to use our imaginations.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Galileo couldn't go to the moon, but we went to the moon in the 1970s, and David Scott, commander of Apollo 15 lander on the moon, named Falcon, was able to show what Galileo knew was the truth, that two objects of dramatically different mass, if you could remove the second-order effects of air, would fall to the ground with the same constant rate of acceleration. Newton was aware of the work of Galileo through Galileo's Discorsi on mechanics, and was to be deeply influenced by this once he had developed his three laws of motion, realized that he could explain why it was that Galileo's law of falling bodies behaved as it did. In the Principia, Isaac Newton formulated what we now call the law of universal mutual gravitation. Gravity is an attractive central force. It is directed towards the centers of objects. The gravity force is also a mutual force. It works between pairs of massive objects. Remember the third law of motion. To every action, there is an equal and opposite reaction. This, too, is embodied in the gravitational force. Finally, gravity is a universal force. It works the same between every pair of massive objects everywhere in the universe. It is this latter part that is most important. For Newton, there was no distinction between the terrestrial realm below the moon of death and decay and the celestial realm of eternal perfection above. As above, so below. The same laws that govern falling bodies on the earth must govern moving and falling and orbiting bodies in this cosmos. Stated mathematically, the force of gravity between two massive objects is proportional to the masses of the two objects and inversely proportional to the square of the distance between them. Expressed mathematically, the force F between two objects with mass 1 and mass 2 is equal to g, the gravitational constant, times the product of mass 1 times mass 2 divided by the distance between their centers squared. This is important. It's not the distance of their surfaces, it's the distance to the center of mass of each of these objects. Notice that the force falls off as 1 over the square of the distance. It is not directly proportional to distance or any higher power, but the square. Why is this? Newton reasoned initially that this was because the force should seem to emanate in all directions from the center of an object, outward upon a sphere. The further you get from the center of a sphere, the more spread out the surface of that influence was, and that surface area scales as the radius of the sphere squared. And so Newton reasoned that if there was an influence, a force pulling equally in all directions towards the center of mass 1, then the further you got away from mass 1, the influence, the strength of that force should fall off as 1 over distance squared. This was a guess, and a very astute one at that. Newton, however, could go further than guess. He could show mathematically that the behavior of objects which under the influence of a different central force law, a force that fell off as 1 over distance, or 1 over distance cubed, or 1 over distance to any power he choose, does not give the direct descriptions of motion. Only a force that falls off as 1 over distance squared does. Let's take a look at the consequences of this inverse square law of force. The first way is let's look at the influence on mass. Gravitational force is proportional to the product of the masses of the two bodies, not the sum, but the product. We start out with our two masses, m1 and m2, whose centers are situated a distance d apart. Keeping the distance fixed, if I was to double the mass of m1, so that now it's 2m1, the force of gravity between them would be g times 2m1 times m2 over d squared, which is 2 gm1 over m times m2 over d squared, or twice the original force. I double the mass of one of the objects, I double the gravitational force felt by a second object of mass 2 at the same distance d. This makes intuitive sense. Double the amount of mass, double the amount of gravity it exerts upon all other massive objects in its surroundings. But it works both ways. If I double mass 2, so it's now 2 times m2, then the force between them is g times 2 times m1 times 2 times m2 divided by d squared. 2 times 2 is 4, so it's 4 gm1 m2 over d squared, or 4 times bigger than the original force between just m1 and m2 set originally. Force is proportional to the product of the masses. I double the mass, I double the force in the system. I have the mass, I have the force in the system. It's simple and very intuitive. The more stuff I have, if gravity is exerted by mass, then it must scale as the mass, but the product of the mass of both objects. Let's look now at the distance dependence. We say that the gravitational force is inversely proportional to the square of the distance between the two bodies. Once again, we have our two masses, m1 and m2, situated initially a distance d apart. The force between them, gm1 m2 over d squared. Now let's increase the distance of m2 and move it 2 times further away. Newton would have told us that the force should be gm1 m2 divided by 2d, quantity squared. 2 squared is 4, and so pulling it outside of the equation, that gives me 1/4 gm1 m2 over d squared. In other words, take the same mass, move it 2 times further away, the force must get 2 squared, or 4 times weaker. Therefore, the 4 appears in the denominator, and the force is now 1/4 what it was when the mass was only a distance d apart, not 2d. I double the distance between two masses. The force goes down by a factor of 2 squared, or a factor of 4. It works the other way. Imagine instead of being at a distance d apart, I move them closer together, so now they're of distance d over 2, half the distance they were originally at d. In this case, the force is equal to gm1 times m2 divided by d over 2, quantity squared. Again, 2 squared is 4, but now because I have 1 over d over 4, d squared over 4, the 4 has got to come up, and I have the force is equal to 4 times gm1 m2 over d squared. In other words, the force is now 4 times greater than it was when the two objects were simply located a distance d apart. This is the essence of the inverse square law of force. The further two objects move apart, the force of gravity goes down. It goes down as the square of the distance. This idea of an inverse square law of force is extremely important. It's going to turn out to be, as I've mentioned before, the only kind of force that is going to correctly describe the motions of objects in the heavens. How now can we understand Galileo's result that two objects of very different masses held on the surface of the Earth and dropped fall at the same rate of acceleration? How does the law of gravity describe the law of falling bodies? What if we drop an apple now on the surface of the Earth? What is the force of gravity on the apple? Well, we just learned that. The force on the apple is g times the mass of the Earth times the mass of the apple divided by how far apart their centers are. When I'm standing on the Earth at human scales, the difference between my shoulders, where I might be holding out the apple at shoulder height, and the ground is very small compared to the nearly 7,000 kilometer radius of the Earth. So to a good approximation, the difference between where my apple is at my shoulder height to an apple down at my feet doesn't change very much compared to the radius of the Earth, so the force on the apple is approximately equal to g times the mass of the Earth times the mass of the apple divided by the radius of the Earth squared. How much does the apple accelerate down towards the Earth when I release it in response to the force of gravity? Well, we know that from Newton's second law. The acceleration experienced by the apple is equal to the force on the apple divided by the mass of the apple. Just the second law. But I know what the force is. The force is given by the force of gravity, so I substitute in for F, g times the mass of the Earth times the mass of the apple divided by the radius of the Earth squared, and of course divide by 1 over the mass of the apple. That gives me the acceleration on the apple. But look, I have the mass of the apple in the numerator and the mass of the apple in the denominator. They cancel. And I get that the acceleration of the apple is equal to g times the mass of the Earth divided by the radius of the Earth squared. Provided I'm standing on the surface and the distance fallen is very much smaller than the radius of the Earth, the acceleration felt by the apple doesn't depend upon the mass of the apple at all, in some sense. It depends only on the mass of the Earth and the radius of the Earth and this gravitational constant g. I haven't said up to this point what g is. For our purposes, g is just a number. G sets the scale, the strength of the gravitational force given a certain amount of mass located a certain distance away. If I was dealing with masses in kilograms and distances in meters, I could express g in units of meters, kilograms, and seconds as 6.67 times 10 to the minus 11 in the so-called MKS units. We're not going to really concern ourselves with the value of g so much in this class, although we will a little bit in some of the labs that you'll be doing. If I put in numbers for the gravitational constant, the mass of the Earth, and the radius of the Earth squared, I can compute that the apple's acceleration should be 9.8 meters per second, which I write as 9.8 meters per second squared. The second squared is just a shorthand way of saying per second. What this means is, as an apple falls, for every second that it falls, its speed gets faster by 9.8 meters per second. It starts out at 0 when I release the apple. 1 second later, it's moving 9.8 meters per second. During this next second, it goes from 9.8 meters per second to twice that, or, wait for it now, 19.6 meters per second, and so on. This is now the explanation for Galileo's law of falling bodies. It doesn't matter whether I've got a bowling ball or a tiny little apple, they're both going to fall with the same 9.8 meters per second acceleration on the surface of the Earth. This explains Galileo's law of falling bodies, but Newton's third law gives us a second and more surprising insight. Remember, the third law states that to every action there is an equal and opposite reaction. Forces come in pairs. We've been concentrating on the force of the Earth's gravity upon the apple. But what is the force of gravity between the apple and the Earth upon the moon? Remember, gravity is a mutual force. The Earth is pulling upon the apple, but similarly, the apple is pulling back upon the Earth. What is the force of gravity on the Earth? Well, Newton tells us it's the same. The force of gravity felt by the Earth is g times the mass of the Earth divided by times the mass of the apple divided by the radius of the Earth squared. So, how much does the Earth accelerate up towards the apple? After all, the Earth has mass and is experiencing a force. Therefore, a mass experiencing a force will accelerate in the direction of that force. We saw the apple being pulled towards the Earth, but at the same time, the Earth is being pulled upward towards the apple. Well, I can write this down by writing down the second law. The acceleration on the apple is the force on the apple divided by, the acceleration of the Earth is the force of the Earth exerted by the apple divided by the mass of the Earth. So the Earth accelerates upwards by the force, Fe, divided by the mass of the Earth. Well, I know what the force of gravity is. That's just g times the mass of the Earth times the mass of the apple divided by radius squared, and now divide by the mass of the Earth. Just like before, the mass of the Earth cancels. And now the acceleration of the Earth is g times the mass of the apple divided by the radius of the Earth squared. If I have a half a kilogram apple just held at shoulder length above the Earth's surface, the acceleration felt by the Earth will be 2.5 times 10 to the minus 25 meters per second. This is a very unintuitive result. After all, 2.5 times 10 to the minus 25 meters per second, a few times 10 to the minus 25 meters doesn't even come up to the diameter of an atomic nucleus. This is a tiny, tiny amount. But Newton demands, if the apple is accelerated towards the center of the Earth must be accelerated towards the center of the apple. How much is the apple accelerated? It's accelerated by the force of gravity divided by the apple's mass. How much is the Earth accelerated towards the apple? The force of gravity between the Earth and the apple divided by the mass of the Earth. Because the mass of the Earth is so much bigger than the mass of the apple, that acceleration is smaller than the acceleration experienced by the apple in proportion to the ratio of their masses. In summary, Newton's third law tells us that the apple accelerates down g times the mass of the Earth divided by the radius of the Earth squared, or about 9.8 meters per second. The acceleration of the Earth in response to the gravity of the apple is g times the mass of the apple divided by the radius of the Earth squared, or as we've just calculated, about 2.5 times 10 to the minus 25 meters per second. The force felt by the apple due to the Earth's mass is exactly the same as the force felt by the Earth due to the apple's mass. The same g times the mass of the Earth times the mass of the apple divided by the radius of the Earth squared. Gravity is a universal force, and it is a mutual force. While this may not seem very important when dropping apples to the Earth, it is of great importance when we consider the motion of two very large objects, perhaps of comparable mass, relative to each other. We're going to look at the consequences of gravity in that case to understand the motion of the moon in the last part of this lecture.